Hello everyone, welcome to AMS Academy. Today we are going to solve this integral. So this is a fractional part integral and I chose this integral because I wanted to explain the properties of fractional parts and I also wanted to explain some properties of definite integration. So by the end of this video you will be feeling comfortable in both fractional parts and definite integration because we are going to use a lot of properties here. So look at this integral carefully first. 0 to 1 fractional part of 1 upon kth root of x. So the whole thing is inside the fractional parts and we have k greater than or equal to 2. Now it might seem impossible for you to even start this problem if you are not aware of the fractional parts. So I will say that fractional part of x simply means it's a number between 0 to 1 where it cannot be 1. And some examples would be 0.2, the fractional part of this is 0.2 itself. 1.5, the fractional part is 0.5, like that. So it basically gives you the fractional part, not the integer part. Okay. Now, how do we do this? So we will begin with the obvious substitution, x equals to t to the power k. So x equals to t to the power k. With this substitution in hand, we can write dx equals to k into t to the power k minus 1 dt. Notice that the limits remain 0 to 1. So our integral basically becomes 0 to 1. Fractional part of 1 upon, now since kth root of x is then t, this simply becomes 1 by t and dx as here becomes k into t to the power k minus 1 into dt. This much is done, right? Now we make the substitution u equals to 1 by t. So this would mean that t is equals to 1 by u, and then if you differentiate both sides it will give you dt equals to minus du by u square. Notice the limits. For t equals to 0, u is infinity, and for t equals to 1, u is 1. Inside we have fractional part of u, k is as it is, let's put it outside, and then t to the power k minus 1 becomes 1 by u to the power k minus 1, and dt becomes minus du by u square. We can simplify this and write this as k 1 to infinity, since the minus sign basically reverses the order of integration here. Fractional part of u divided by u to the power k plus 1 du, and we reach this point, and that is the goal in every fractional part integral of this type. We have to reach something where we have the fractional part in the numerator or the denominator simply as u. Now let's do it from here. So we have this integral now. Now in this integral, notice that fractional part of u, the important property to notice is fractional part of u can be written as u minus the integral part of u. This is the property of fractional parts. Now the integral part of u is basically given by the greatest integer function, and you know that for greatest integer functions, if you put in 1.2, it will give you simply 1. It will always give you the integer, the greatest integer less than or equal to the given number. So that is why fractional part can be defined like this. Okay. Now what we are going to do is we are going to abuse a property of integrals, that it can be broken down into intervals. We are going to break this down into intervals like 1 to 2, plus 2 to 3, plus 3 to 4, and so on. Infinitely many integrals, as you can see. And inside always we will have the function u by u to the power k plus 1 du. Now how to write this formally? What you can do is, since all these integrals would be additions because we are breaking it down, we can simply write k into summation n equals to 1 to infinity, and then integrate from n to n plus 1. What we are integrating? U by u to the power k plus 1 du, correct? Now we can write now this as n equals to 1 to infinity. Since this u is basically equal to this, we can write n to n plus 1. This as u minus the integer part of u inside the interval n to n plus 1, where n and n plus 1 are integers, is simply n, because n is the greatest integer that is less than n at this interval, right? Because u right now is between n to n plus 1, so integer part of u would be n, right? It is n point something or n. So u minus n, where this part is n, divided by u to the power k plus 1 du. Okay. Now we can integrate this like this. So k summation n equals to 1 to infinity, integration of n to n plus 1, and break it down as like this: 1 by u to the power k minus n by u to the power k plus 1 du, and we reach this point. And now after this we can evaluate it again. Okay, so now we have this integral, and if we can find out this integral and then finally evaluate the summation, we will get our answer. Okay, what we can do is we can write this as k summation n equals to 1 to infinity, and now we have to basically find the antiderivatives. You can use the standard power rule and everything inside the summation. So the first one basically turns like this: u to the power minus k plus 1 by minus k plus 1, and this would be evaluated from n plus 1 to n minus n times. Similarly, u to the power minus k minus 1 plus 1 minus k minus 1 plus 1, and evaluated from n plus 1 to n. Correct? Now write this as k summation n equals to 1 to infinity. Now the first one, what we can do is this: we can put n plus 1 here. So we can write like this: n plus 1 to the power, well, this would be k minus 1, and there is a 1 by 1 minus k common to both of them, so we'll just simply do this here, n to the power k minus 1, and this is multiplied by 1 by 1 minus k minus n. As you can see, this is basically minus k, so is this u to the power minus k. So again minus n, and this minus k, this goes to plus n by k, which is common, and then again we do the same thing: n plus 1 whole to the power k minus 1 by n to the power k. Now this is the summation that we have to evaluate here. Okay, so k summation n equals to 1 to infinity. First of all, this 1 by 1 minus k can be written as minus of 1 by k minus 1. So we should arrange the terms together and then look for how to do it. So this term would basically be 1 by n plus 1 to the power k minus 1 k by 1 minus k minus k by 1 minus k summation n equals to 1 to infinity 1 by n to the power k minus 1.
Bas. Start.
So plus summation n equals to 1 to infinity. Now this term 1 by n plus 1 whole to the power k, and then you have n by k into k, which simply gives you, there is also n here actually, and k and k cut off basically, and then again you have this sum where you have plus I think minus summation n equals to 1 to infinity n by n to the power k, which is 1 by n to the power k minus 1, and this is our final summation which we have to evaluate. Okay, so this is the final form which we have for the problem. Before starting this, remember that zeta of p is a number. This is called a zeta function, which is the Riemann zeta function. There are other zeta functions as well. This is defined like this: 1 by 1 to the power p plus 1 by 2 to the power p plus 1 by 3 to the power p, and all the way up to infinity. And in short, in summation notation, you can write this as n equals to 1 to infinity 1 by n to the power p. So this is a standard function, and all even values and almost all odd values of zeta functions are all known. So all even values can be expressed in terms of pi actually, but odd values are irrational and they do not really have a closed form. But okay, we are going to use zeta to give our answer because this is accepted as a closed form answer. Now look at this sum here. So I then would be equal to k by 1 minus k, and this sum here, you see that n equals to 1, that means this sum starts from 1 upon 2 to the power k minus 1 and it goes up to infinity. So basically starts from this point and goes to this point. So if you take from this part, this basically equals zeta p minus 1, right? So what would this equal? This would equal zeta of k minus 1 minus 1, because the power is k minus 1, which is p here, right? Okay, similarly minus k by 1 minus k, this one is directly zeta of k minus 1. So this one is directly zeta of k minus 1. Let's come down here. This we can write down as plus summation n equals to 1 to infinity. Write n as n plus 1 minus 1. So introduce a plus 1 and a minus 1 here. So that n plus 1 and this cut off, and it gives you 1 by n plus 1 whole to the power k minus 1, and minus 1 gives you this, n equals to 1 to infinity 1 by n plus 1 whole to the power k, and the last one is simply zeta of k minus 1. Okay, let's do this. This k by 1 minus k into zeta k minus 1, and this one cut off, and we have simply minus k by 1 minus k, right? And from this part we have plus zeta of k minus 1, and this part again n equals to 1, and this is n plus 1. Okay, so this is zeta of k plus k minus 1 minus 1, because this also starts from 2, and minus this one is also zeta of k, right? And this is also starts from 2. and at the end we have minus of zeta of k minus 1. Okay, absorb the minus here and you get k by k minus 1. You see that this zeta of k minus 1 and zeta of k minus 1 cancel, the minus 1 and the plus 1 cancel, and you have minus zeta k. So the answer stands this, k by k minus 1 minus zeta of k. For k equals to 2, the value of zeta 2 is pi square by 6. So if this was a function of k, you can say, then I2 simply equals 2 by 2 minus 1, which is 1, minus pi square by 6, which is the value of zeta 2. So this was a very tough problem, but it introduced you to all the aspects of summation and how to interchange between summation and integration, and use these functions like zeta p and the p series basically. So if you like this video, and let me know in the comment section if you want more content of this type, and also if you have any doubts, please let me know that. Also subscribe to the channel and follow for more. Thank you.